All right, anybody else? All right, so let's go through this problem. What did y'all think? Was this fair? Or?
Yeah.
All right, I think if you did your homework, then you would hopefully agree that that's a fair quiz. So you need to bring your formula sheets to class. I've told you that already. I wasn't kidding. And you need to do your homework. Because if you did your homework, you would have run into something like this, and it works out really nice, actually. All right, so we're going to apply the product rule right here. And then this is a separate term, so we can do the derivative on that separately. Product rule here, derivative of x is 1, so then times tangent hyperbolic inverse of x plus product rule, right? Derivative of tangent hyperbolic inverse. So it's on what page on your reference sheet here? Page 5 has all these derivatives, and it's formula number 33. And it says it is 1 over 1 plus minus x squared. And in this particular problem, because the argument is x, then it's directly the formula. There's no chain rule that has to occur. But then we have to multiply by the x for the product rule. So I'll just tack that on times this x. So that's done with the product rule. Now I move on plus, not times, the derivative of natural log of the square root. So 1 over just the square root of 1 minus x squared, then times the derivative of what's in the natural log. So the derivative of a square root of something is 1 over 2 roots of 1 minus x squared. Then the derivative of what's inside, which is negative 2x. These twos cancel, right? You have tangent hyperbolic inverse, you have plus. This right here becomes x over 1 minus x squared. And then this actually turns out to be really nice, because this root times this root, you square it, the root goes away, you get the 1 minus x squared on the bottom. And on top, what do you have? Negative x. Or you could say minus x over 1 minus x squared. Right? That's what this turns into. And these cancel each other out. And your answer's the hyperbolic tangent inverse function of x. So I'll be looking for partial credit. I mean, I'll be looking to see if you got this, but maybe you didn't simplify it properly, you know? But I need to see work, okay? It can't just be, I know some of you have computer algebra systems, your calculators can take derivatives, and that's not the point. The point of this is to be able to do this mechanically by hand, illustrating that you know how to apply chain rule, product rule to these new functions, right? Okay, so I have a different sort of camera setup today, so I hope it's not too obstructive for you. If it is, let me know, all right? Because I can't stick with it if people can't see. But what's good about this camera, I think, I'm trying it out for the first time, is that I get a wider field of view. So I actually can go from this bar to that bar. It's a little bit wider. It's about 1.5 feet each way. So I'll give a little more space. And I can also, I can move it, like I can rotate it. So I don't need to worry about hiring you, Ron, right? I don't have to hire Ron to move my camera for me. Okay, let's move on. Y'all ready for today's stuff? All right, let's do it. So we're gonna go to chapter 4. So we're gonna jump here now. We're done with the stuff from all the trig stuff, the inverse hyperbolic stuff. It's all done. So let's see how this camera works out. Haven't tried this yet. You're my guinea pig class. So I have no idea what's going to happen here. Can somebody kill the lights over there for me? It's motorized, yeah. All right. Man, I cannot.
I expect you to edit that out.
No, it's
What's that? Yeah, you're not in
It's
there.
the thingy right here.
Yeah, that's the viewfinder.
Yeah, I can't make out that on the board. I wonder if it's coming out on my camera up here. It's coming out okay. We'll do that. All right. So let's go through these notes. All right, this is where we kind of start really the Cal 2 idea, the antiderivative. All right, so we talked about this in the beginning. Said first part of this, we've just still been focusing on derivative chain rule and all that. Now we look at something called the antiderivative. So if you have a function, which we're going to call capital F, it is called the antiderivative of another function, little f, on an interval I, if the derivative of capital F is the little f, for all x in some interval I. All right, so what the heck does that mean? It's just a way of relating two functions together. One of them is a function, the other one is the derivative of that function. So what we're used to seeing, right, what we're used to seeing is like someone gives you a function little f, you take the derivative and we called it f prime, right? Now what we're going to do is we're going to give you a little function, or a function little f, and we're going to say that is the derivative of some other function. It came from something. The thing it came from, that it is the derivative of, is kind of like its parent, okay? And that's its antiderivative, and we call it capital F. If capital F is an antiderivative of little f, then capital F plus c is the most general antiderivative possible. All right, where c is any constant. We call this later the constant of integration. So let's just take an example here. All right, so here's an example. Little f of x is 2x. Does everybody agree that the antiderivative of little f is this capital F of x, which is x squared plus some number? Yes? Because if I take the derivative of this one, x squared plus c, everyone here would say the derivative of x squared is 2x, the derivative of a constant is 0, and so you would tell me that the derivative is this right here. So big F is the antiderivative, the most general antiderivative of 2x. Now graphically, the red line here is 2 times x, right? That's 2x. This blue parabola is just one of the antiderivatives of little f. We said it could be this x squared plus any number. So I could change the value of c. Notice I have x squared plus 4 now. And all it's doing is shifting that parabola up and down. Any function there, any of these, would qualify as being an antiderivative of 2x. So we actually have an entire family of functions. There's how many of them? Infinitely many, right? You have an infinite number of antiderivatives of 2x. So just keep that in mind. When we were in Cal 1, we had a function, we took its derivative, the answer was just a single function. Here now, when we start with the function, we try and find an antiderivative, we get an entire family of functions, infinitely many of them. All right? So here's another example. If little f of x is 3x squared plus 10x plus 6, then does everyone agree that this is an antiderivative? So how could you check? Just take the derivative of this real quick. Derivative of x cubed is 3x squared. Derivative of 5x squared is 10x. Derivative of 6x is 6. And then we always throw a c on there because that gives us the family of functions. And again, here's the picture of what's happening. All right? So there, the red one is the parabola. That's little f. Capital F is a cubic function. This is the blue one. And we have all those possible, the family. There they are, right? Now this one I did something even more. I want you to see why this works. Remember that if I start with the function, the derivative is the slope of the tangent line, isn't it? Notice that on every single function in this, this family, the slope of the tangent line at that point, aren't they all parallel? Which means that it doesn't matter which function I pull from that family, the derivative at that point is always the same. And that holds for every point. If I slide this around, you see, anywhere I go on that family, the derivative is always equal, which is why they all share that same derivative. What is it? 3x squared plus 10x plus 6. Does that make sense visually? Okay. Okay, so now what we want to do is we want to look at this table. This is in our book. It's on page 249. I don't know if this is in your notes. Is that in the notes? It's not, right? I think I added that the other, like another semester. I haven't updated the notes. But this is a table that's in your book. Right now, starting right now, everyone needs to be aware of all of these connections between little f's and capital F's. So let's see how many of these we actually know. When we took derivatives, what did we always do with constants that were in front of functions? When we took derivatives, we just carried them along with us, right? Well, same thing with when you're trying to find an antiderivative. If you have a function and you have a constant in front of it, don't worry about the constant. Just find the capital F and just slap the constant to the front, all right? If you have two functions being added together and you want to find their antiderivative, you can find the antiderivative of each one, can't you? That was the same way with derivatives, right? You have two functions, you want to take derivative, you do derivative of each one. So that rule works backwards also, which is nice. Okay, this one we're going to talk about a little bit more here in a second, and this one we're going to talk about in a second. But how about this? E to the x, what's the antiderivative of e to the x? Itself, right? Because derivative e to the x is itself. The antiderivative of cosine x would be positive sine x, because remember, you're working backwards, right? And just think through it. What's the derivative of sine of x? Cosine x. So when you go backwards, cosine to sine, it doesn't change signs. But sine does. The antiderivative of sine x is negative cosine x. And then these, again, from Cal 1, antiderivative of secant squared. Well, what do you take the derivative of to get secant squared? Tangent. So the more you know, the more you actually know from Cal 1, the more of those things that you've got memorized, the easier it's going to be for you to go backwards. All right. I showed you this one. What was it? The first day or second day? First day? I don't recall. But the derivative of inverse tangent was 1 over 1 plus x squared. And I put it over here on the side of the board. I said, remember that one, right? It's going to show up a lot. So just remember that. When you see 1 over 1 plus x squared and you work backwards, the antiderivative would be arctangent. Okay, you can look at the rest. We're going to do these examples. But before we do it, we've got to establish something. So let me move my camera back over to me. It's a little slow, huh? Remember, I'm doing this only because of the internet students, you know, like having to record that. All right. Okay. There we go. That should be it. All right, so let's work through these examples. I'm just going to work them off the board. We have, let's see how far I got here. Somehow my line got off. Where's my hand? There it is. Okay, first example, A. We have, f of x. Let me write it down and then we'll talk about it. We'll talk about how we're going to come up with this general formula. All right. Man. All right, so what do we know about Cal 1 when we took derivatives? If I gave you x to the n in Cal 1 and I said take the derivative, you would say bring the power down, right? N and then you would subtract 1 from the power, wouldn't you? So to do an antiderivative, we know that to get back from some power of x to get back, we're going to have to undo that taking away of 1, right? So we're going to need to add 1 to it. So what we're going to try and do is come up with a general formula right now. If little f of x is equal to x to the n, I want us to find capital F of x. And this is going to turn out to be the formula that we're going to put up. Okay, we're going to put this formula up on that sheet. It's on that table. I'll go back to it and I'll just make sure everyone is aware of it. Okay, so we said capital F of x, the power would have to be what? 1 more than that, right? So n plus 1, we'd have to add the power. And then we would always need to add some constant to get the general antiderivative. But is this enough? So let's just check real quick if this works. Let's try it on something. I'll do an example over here. Let's say little f of x was x cubed. Is our formula good? Capital F of x equals x to the 4th plus c. Is that going to work? No, because when you take the derivative of this, first thing that happens is that 4 comes out. And we don't want the 4, do we? So how do we eliminate that 4? We divide by 4, right? We just need to take this, and instead we would need a 1/4 here, wouldn't we? And then when the 4 came out, it would wipe out the 4 and we would have the x cubed, yes? So that's exactly what we're going to do in our formula. Out here in front of this, we're going to scale it or multiply it by 1 over this power, n plus 1. Now, every time we take the derivative, the first thing that happens is the n plus 1 comes out, and then it cancels. And then the next thing that happens is we reduce the power by 1, that becomes x to the n. And then derivative of a constant is 0. Does that make sense how that would work? Okay. So that looks like this formula will work, okay? This looks like a formula for us, but there's one problem. There's one issue where this formula falls apart. If what? Not x. If n is -1. What if n is -1? Then wouldn't this formula give you division by 0? So this formula does not seem to work if n is -1. So I need to state that over here somewhere. Somewhere maybe at the end here, or I'll put it down here, for n not equal to -1. So as good as my formula is, it won't work for that one case. But let's look at that one case. What if n is -1? Then what's little f? So if n equals -1, little f of x is actually x to the -1. Okay, x to the -1, which is 1 over x. And that's one that you should remember from Cal 1. The derivative of what gives you that? Natural log. So capital F of x would be equal to natural log, and we put absolute value of x so that we don't have any problems with negative numbers, plus c. So this resolves all of the possibilities when it comes to powers that we could have on x. So if you go back and take a look at that table I had up here, right there, x to the n, what's the antiderivative? They wrote it this way, right? Instead of writing it like this, they wrote it x to the n plus 1 over n plus 1. Isn't that the same exact thing though? Yes? So, and that's what you do if n is not equal to not equal to -1. And then the next formula down, 1 over x, is when n is -1. Make sense? This works for every power of x now. We can do anything. So now let's do part A. Can we get lights, please? Seems kind of dark in Oh, no, no, on, please. Good try. Try and take a nap. All right, so I know that some of you have seen this before, I know for a fact, but just hang tight. It's going to speed up quick here, okay? You're going to find yourself going from bored to confused very quickly. So don't fall asleep on me. All right, so if we're going to use the power rule, right, this power rule for finding antiderivatives that we just established, then when we look at things, we need to make sure that we have powers of x, which in this case we do, right? Every one of these three terms is a power of x. We just have to kind of make sure we get it written down first. So the first one, 2/3 x to the third, that's a power of x. How can I rewrite this one, Matthew? Hold on, Matthew.
4x to 1.
Matthew? I'm just giving you a hard time, Kiki. To the 1/2? Yes? Okay. And then, Kiki, all right, I'll give you an opportunity now.
No, it's too late.
Too late? The window's closed?
Yeah.
Okay. Then who's going to do it for us here? What's the power of x there? That half is on this, but x to the 3/2. So yeah, this is x to the first power. This is really x to the half power. You add the powers, it's 3/2. X to 3/2. And so now what you have three terms. Each one of these is x to a power, x to a power, x to a power, so we can use our rule. Right? What about the numbers in front, like the 2/3 and the 4 and the -1? What do we do with those?
They're constants.
They're constants, so we're going to just bring them with us, right? We're just going to bring them with us. So here we go. Capital F of x will be equal to a bunch of stuff in here plus c. I'm going to just throw the c out here now just so we don't forget it. All right, 2/3 first. And now, Ruben, behind you. Who's that? Vanessa, where's your thing? Okay, so that's why I'm calling on you. If you forget it, I'm going to call on you. Did you have one still? I have extra paper. You know extra paper? All right. What's up? Okay, Vanessa?
Yes.
Okay, Vanessa, can you give me the antiderivative of x cubed, please? Using the formula that we just established. Here you go. Mm-hmm. No? What's going to happen to the power? It's going to go up by 1. Okay? So x to the 4th. And then what do we have to scale by in front of it? 1/4. 1/4. Next one, +4. All right. Ron, you look bored. I'm going to ask you for the next one here, Ron. Right here, x to the 1/2. So what's the power on the x? I'll start with the power, if that's okay with you. Is that all right if you just give me the power first? 3/2. So you're adding 1 to 1/2. And then what about the number in front?
2/3. Or, I mean, it's going to be 2, but reduce this down to 6.
So you have 1 over, you're doing 1 over this number, right? You were right the first time. Yeah, 1/3/2. This is n plus 1, right? What's 1/2 plus 1? 3/2. So that's the power. And then this is always going to be 1 over that power. So 1 over that. But 1/3/2 is the same as 2/3, which I'll write on the next line. Minus x to the 5/2 is the power. And the number out front is 1/5/2, which will be 2/5. And what you do is eventually get to the point where you don't do the 1/5/2. You just do mental, flip it in your head, 2/5, and you're good. All right, let's put all this together. I have a 2 reduces here. So I have 1s across the top and 3 times 2. So I have 1/6 x to the 4th. See, what do I have here? 8/3. Flipping and then multiplying. 8/3 x to the 3/2. And then finally minus 2/5 x to the 5/2. Plus my constant. And then I box this up. That's my general antiderivative of that function. Now, the good part about these antiderivatives is that you can do what? You can check your work, right? You can actually check your answers. And you would check it by doing what? Taking the derivative, which would be relatively easy to do with this. All right, that's part A. Okay, let's look at part B. How many of you covered the antiderivative power rule in Cal 1? That's it? All right, the next one, little f of x is 2x plus root x minus 4 plus x cubed. Over cube root of x. Now, yeah, I'll put cube root of x. You must be very careful here because we had in that table, we had a rule up there that told us what we could do when we had addition between two functions, right? The top left, f plus g, that said that you could then split it up and just do the antiderivative of each one, right? Is there any rule up there that tells you how you can handle something when you have division?
You can split it up.
Okay, you could split it. I think you mean like put this over this, this over this, this over this, this over this. Yes, and that's what we will do. But what you cannot do is just ignore this and take all these antiderivatives and then just divide by whatever the antiderivative of that is. You cannot do that. All right? It's not allowed. Now, why isn't it allowed? Why don't you think, why is it that if we have little f of x, little g of x, why is the antiderivative not capital F of x over capital G of x? Why do you think that it's not that? Check your, yeah, if you were to check your work, what's the derivative of this? Quotient rule. And the derivative of that would not be this, would it? And that's what made Cal 1 difficult, is because when we got to the quotient or products and quotients, we realized that the derivatives weren't as nice as what we wished they would be. So it's the same thing in Cal 2 when you're trying to go backwards. It's easy if it's just term, 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 term. But if it's division or products, therein lies the problem. And we haven't really gotten to that yet, but that's where we're headed. And that's where we'll spend the next couple of weeks, trying to figure out ways to go backwards when we have complicated looking expressions. All right, but this one we can still handle with the power rule if we first realize that we have a single term in the denominator, multiple terms in the numerator, and just properties of fractions allows me to just split this up into 4 different fractions. And I'm also going to convert everything over to rational exponents. Rational exponents means fractional exponents. We good? Just wrote everything as fraction. Now let's rewrite each of these terms as a power of x, because all of these can be simplified, right? Like x over x to the 1/3 can be simplified, that can be simplified. This one can be brought up, can it, as a negative exponent? And then this one also can be simplified. And we subtract the exponents, don't we? Like we do 1, take away 1/3. We do a half, take away a third. Here we just bring it up, and then here we do 3 minus a third. Agreed? All right. So we have not done an antiderivative yet. We're just trying to simplify this. So what is my first one, Chris? Testing. Oh, hold on. This, Chris. Or I'll let you both have an opportunity. What do I do with the 2? Okay, 2. So I'm not doing antiderivative. I just want to know what the powers on x's are. So x to what? Testing your fractional. 2/3. So look, you've got to get good with these fractions. It's got to be quick. All right, and now you might need to scratch paper. That's okay maybe in the beginning, but you really, as a Cal 2 student, you should be able to do the basic arithmetic of fractions like these, maybe mentally, if that's not too much to ask. Who's going to give me the next one? X to the 1/6. Everyone agree? Okay. So just plus x to the 1/6, like that. What's the next one? Minus 4x to the negative 1/3. And finally, plus x to the, what's 3 minus a third? 8/3. That's just what little f is, right? We still have not found capital F. So now we have the pleasure of finding capital F. Capital F would be, and now we do each one of these, the 2 is going to come along. Zach, what do you think about the power on capital F for this one? How are you feeling with the fraction power stuff? Feeling? What? I'm doing the antiderivative, right? So I'm going to use a power rule on this, which means I'm going to add 1 to this power. Are you comfortable adding 1 to 2/3? 5/3? And then what has to come in front of it? 1 over 5/3, but that's really 3 over 5. So 1 over 5/3 flips and becomes 3/5. And that's really what we try and get to a habit of doing. Do y'all understand that? 1 over 5/3 is really 3/5. The 2's just sitting out there waiting to mess with it later. Dustin, did I call on you? I haven't called on you, right, Dustin? All right, so Dustin, how do you feel about x to the 1/6?
6 over 7, x to the 7.
Good. 6 over 7, x to the 7/6. So if you take 1/6 and add 1, you get 7/6. 1 over 7/6 flips and becomes 6/7. Can I get a single person to volunteer for the next one? Anyone want to volunteer?
11/3.
Okay, right here. We're doing this one. So minus 4. What is it? 2/3 or 3/2? What I'm hearing two different things. 2/3? 3/2? Uh-oh. Okay, let me do the power first. What is the power? Take negative 1/3 and add 1. 2/3. Which means the number out front will be that flipped over, so 3/2. And last one. What's 1/3? What's 8/3 plus 1? 11/3. And that means out front? 3 over 11. 3 over 11. 3/11 plus C. Now that plus C needs to be written if you're asked to find the general antiderivative. I will count off if you forget it, but I won't count off a lot. Like, if it's a 10-point problem, I'll count off 1 point. But please be aware that there are some instructors that are extremely critical of that plus c, and if you miss it, they'll count the whole problem wrong. It's that important to understand that it is a family of functions. All right, so you could clean this up now, right? Let's just look at what would change on the next line. I'm not going to write it all out. What does this become? 6/5, and then this doesn't change. How about this one?
6x.
Minus 6, and then x whatever, and then that doesn't change. So the next line, everything, the only thing that changes are the things that I circled. Okay? That's it. We're done. Questions? All right, let's look at C. We have, this one's pretty straightforward. F of x equals sine x plus secant x tangent x. So these are not powers of x, right? These involve trig functions, so we better know the antiderivative of these if we have any hope of figuring it out. We do have addition, right? So I can split this up and just look at each one individually. What is the antiderivative of sine x? Negative cosine x? Correct. Then here we have a product, don't we? So you are not allowed to just do each one. But you could kind of, hopefully from Cal 1, remember, secant x tangent x was the derivative of what? Secant x.
Well, negative secant x tangent. So that would mean that it would be.
No, it keeps the same sign. The derivative of secant x is secant x tangent x. You're thinking cosecant x. Derivative cosecant x is negative cosecant x cotangent x. So what would this be here, the antiderivative of this? Just secant x plus c, and we're done. That's it. So there wasn't a whole lot of work to do with this one. It's just recognition of things that we've seen from Cal 1. Now D is a little more involved. Now, I'm not going to really expect anyone to know right off the bat how to do this one, but I would like to ask some people what they are thinking. Yes?
Maybe substitute 2 plus 6 squared.
How do you mean? What do you mean?
Maybe not. Well, I was looking at it because I saw the 1 plus x squared on the bottom. I was thinking that might be possible.
Substitute, though?
Oh,
I'm not
wait, no,
quite
don't
sure what you mean.
substitute. Split them and then have the 1 over 1 plus x squared times 2 plus x squared. I mean, not times, plus. No.
So you're thinking split, maybe?
Yeah, split it so it's 1 plus, or not 1 plus.
The only way I could split this right now is to put 2 over the entire thing plus x squared over the entire thing.
Okay.
That's the only way I could split that fraction apart.
Okay.
Because you got to keep the whole denominator. You can't split, I mean, you can't do this and this, right? Okay. Anyone else have an idea of what we could do? Am I allowed to just say, hey, the antiderivative of the top, and then the antiderivative of the bottom? And then I'm not allowed to do that? Someone's going to do that on a quiz or a test. I know somebody in here is going to do it. Every semester, someone does it that way. So you're all agreeing that I can't do it that way, right? Okay. Yes?
We split it and then we take the denominator to the numerator with the power of -1?
You could do that also. So you're saying split it and then do that?
Yes.
You could. What's being suggested is we do, here's the splitting if we did it, right? And then you could bring the entire denominator up and it would look like this. And then this one would be x squared to 1 plus x squared to the -1. I think that's what you meant, right? This is correct. This is the same expression, isn't it? But how do you handle taking the antiderivative of this? So you cannot take the antiderivative of each one of these individually because again, it's trapped inside of this negative 1. These have to be completely freed up in just a power of x, power of x, power of x, not inside of something for you to do the rule. So we're very limited here, right? Yes?
Can you split the 1 over 1 plus x squared and then take the natural log of 1 over 1 plus x squared?
You mean look at it as being the derivative of the natural?
And then
Could you take 2 plus x squared and times it by 1 over x plus 1 squared, and that would give you tangent?
Take this and
Times it by 1 over that, the denominator.
multiply this by 1 over this. Like rewrite it to look like this. Okay, so that would be the same expression, wouldn't it? Yeah? Does everyone agree with that? And I would probably need to put parentheses around this because that's that whole thing, right? So this isn't a bad idea, but we're still going to run into a problem because look, could you find the antiderivative of this? Yes? That's just the power rule in each one, right? Could you find the antiderivative of this? It's arctangent. Here's the problem. You can't go backwards from here. You cannot go to the antiderivative. If you have a product, you cannot do each one separately. Just like when we had a quotient, you can't do each one separately. And it's because the product rule doesn't work that way either. So I thought I silenced this phone. Our hands are really tied when it comes to finding antiderivatives. Right now, we have to have pluses and minuses between things, and each one of them has to look really, really nice. That's our limitation right now. See, this is the inherent problem in this class, is that in Cal 1, product rule was complicated, and quotient rule was complicated. So now we're trying to reverse the process. So anytime we see a product or a quotient, it's going to be extremely difficult. Understand? So life would be great, and Calculus 2 would not be as hard as they say it is, if you could just say, all right, take the antiderivative of that, done, let's go. Right?